Good afternoon, everyone. We are today looking at 11-1 polar coordinates. Now, you've dealt with polar coordinates in the past, but you just really didn't know about it. Anytime in science that you were dealing with vectors, they had direction and magnitude. That is, in essence, a polar coordinate. Radar uses polar coordinates to locate objects in space or on the water. Structural engineering really uses polar coordinates to evaluate the forces acting on trusses and beams and joists and whatnot in a building, columns, everything. So, polar coordinates very, very useful. Let's take a look at what we dealt with on our unit circle with a 30-degree angle, hypotenuse of 1, right angle, of course. Coordinates out here were square root of 3 over 2, comma, 1/2. We can just as easily say, oh, and I should back up, these are rectangular coordinates. We can easily say, for the same location, we can start here at 0, 0. We can go along the hypotenuse 30 degrees for a distance of 1. There we go again, direction and magnitude, 30 degrees for 1. We arrive at the same location, but in this case, we just give polar coordinates. Polar coordinates of our distance r1 and our angle theta 30 degrees. And we get the same place. It's just another way to look at how we get where we go. Just like driving in your car. If you're crazy, you can drive cross country through the potholes and you arrive there. If you're more civilized, you drive down Monmouth Street, hang a left on Talmadge Road, and you get there maybe in one piece, maybe not. Okay, so there's an example in the book that I feel compelled to talk about because it's not real straightforward. Usually I just let you study your examples on your own and ask questions, but this one I can see you're definitely going to have questions for. And this is example 4. On page 398. And the author really jumps around, and I am pretty certain this might be beneficial to you. So it says, find a rectangular equation for r equals 2 sine 2 theta. That's a polar equation whose graph was shown in example 3. Well, that part doesn't matter. You can look at the graph in example 3. It's a nice little 4-petal rose. But if they want a rectangular equation for that, that might be a little bit tougher. So you start with r equals 2 sine 2 theta, and then they just automatically go to r equals 4 sine theta cosine theta. And what they did was skip from back in 10.3, I believe it was. So we'll say recall from 10-3, we had one that said sine 2 theta equals 2 sine theta cosine theta. I don't know if you remember that, but you can look it up. It's back there in 10.3, I believe, double angle formulas. So right here, we have 2 sine 2 theta. So if we just multiply everything here by 2, both sides of the equation, we can get 2 sine 2 theta equals 4 sine theta cosine theta. And that's where the author is going with that. Now, further, and then the next one might hit you too, I don't know. Remember way back when we did, here's some angle theta, and we talked about the sine being opposite over hypotenuse. We talked about the cosine being adjacent, the length of the adjacent side over the hypotenuse. Okay, so we're going to change that just a little bit now. We're going to say the hypotenuse, we're going to call that r for the radius, which is cool, just like on your unit circle. And the opposite side we'll call y, which is cool because it's a vertical line. It's the y direction. It's not that different. And you probably guessed it by now. The adjacent side we'll call x. That's not so bad. So now we could say that sine theta is simply y over r. Cosine theta is simply x over r. And you can see that because sine theta was opposite over the hypotenuse, y over r. Cosine theta was the adjacent side over the hypotenuse, so that's x over r. And let's just bring in the other stuff we had here, equals 4 times y over r times x over r. And then it's not so bad. So then we would have 2 sine 2 theta equals 4 yx or xy, it doesn't matter, over r squared. Okay, and that's not so bad. But remember, up here in the beginning, we had 2 sine 2 theta was equal to r. So we can bring that in now. R equals 4, and I got to do it, xy over r squared. Can't bring myself to be out of order there. So now we have r equals 4xy. I didn't want to do that. Just wanted to clean up my r a little bit. 4xy over r squared. Getting better. So now, you probably guessed it, we can multiply both sides by r squared, which is what the author did. And that part I think you probably got okay. And we get r cubed equals 4xy. Now let's keep in mind our goal here is to get rid of the r and have something just in terms of x and y. That would be going from a polar equation to a rectangular equation. So, and I think you're okay here, but then the next one might have blown you away a little bit. We've got to do another little recall out here. Recall, Pythagorean theorem says x squared plus y squared equals r squared. And we're used to that. X is just one side of this triangle, y is the other side. They're both legs, they're not the hypotenuse. So x squared plus y squared equals r squared. Okay, so we're good there. So now instead of r squared, we can substitute in the x and the y. We can say x squared plus y squared cubed equals 4xy. Looking good. Now, here's where the author got a little wild by saying that, and it's not too wild, but it's just this part here is not actually r. This was r squared. And so you got to notice that this is the square root of this part. I think that's what would throw a lot of people. So this now is just r. And maybe I can help you see that by writing over here the square root of x squared plus y squared equals r. And actually, it'd be plus and minus the square root if you're really getting technical. Hopefully, that'll help you out a little bit. So now we're at r on the inside here, cubed equals 4xy. Okay? Now, I'm going to go a step further and swap these. And this might make you a little uncomfortable, but I think it'll make it better. Okay? So now I can say x squared plus y squared to the 1/2 to the third equals 4xy. Okay? So far, so good. Now, recall your order of exponents, your rules of exponents. We could say that this is the same as x squared plus y squared to the 1/2 to the third. Remember what we did with these exponents. We had to just multiply those exponents. So now I'm going to write this as x squared plus y squared to the 3 times 1/2 equals 4xy. I'm doing this on purpose. I know it seems like a long, crazy run, but I gotta believe this in the end will make it more accessible. So now I'm going to bring these back in like this. Because if I can say 1/2 times 3, I can also say 3 times 1/2. So now this is x squared, the quantity x squared plus y squared to the third power, or cubed, to the 1/2 power, which is also square root. So now I really don't like this. So I think to get rid of this, I'm going to square both sides, which would give me, I want to go to blue, stick with blue, x squared plus y squared cubed equals 4xy squared. Notice I squared both sides, and that got rid of the 1/2. Okay? So we're looking good. We're looking good. So now let's work on this as much as we can. X squared plus y squared cubed equals, that would be 16 x squared y squared. And I think we're done. And hopefully that's a little clearer than what the author did in example 4 on page 398, because when I first read that, I thought, oh man, that may confuse some of my students. You all are really bright, and you impress me all the time, but I thought I better expand on that a little bit. So here's a rectangular equation. We started with a polar equation. What did we start with? Way up there. R equals 2 sine 2 theta, and we converted it into a rectangular equation. X squared plus y squared cubed equals 16 x squared y squared. Not bad. So thanks for listening today, and I hope this was helpful. Please read through section 11.1, work the examples, and have some questions for me tomorrow. That is all. Talk to you later.